All right. So for this video, this says 7.3.1. A couple things. We are skipping 7.2. Just not important at this point in time. And then this is the only video that's going to go with 7.3. I know it says 7.3.1, but there will not be a 7.3.2. So in about 15 minutes, we'll be done with section 7.3, which is pretty sweet. Today, the last two videos, 7.1, 7.1.2, were about exponential growth and decay. Today we're going to talk about logarithms, which is a new type of function. We're going to talk about what a logarithm is, how it works, and where it can be useful. So, as a quick warm-up, a population of squirrels in a forest increases by 21% per year if there are currently 5,200 squirrels. Is our start value. How many will there be in the year 2030? So we are increasing, which means I'm going to have exponential growth. And just to remind you, this was our exponential growth equation, where P is the starting value, R is the percentage as a decimal, and T is the time, most of the time in years, and in this case, that is true. So I'm starting with 5,200 squirrels. 1 plus the percentage change. It's going up by 21%, so that's 0.21. Don't forget this has to be a decimal. Okay, you have to change your percentage into a decimal, which either means you are moving the decimal point twice or you are dividing by 100. And then to the power of, in this case, we're going to go with 10 because 2030, we're in the year 2020. So it's 10 years later. I'm going to type that in my calculator, 5,200 times 1 plus 0.21 to the 10th power is 34,982.999. But again, we're talking squirrels, so we're just going to go 34983, 34,983, which is a ton of squirrels if you consider that it started at 5,200. Lots. Okay, so what is a logarithm? Okay, just like division is the inverse or the opposite of multiplication, subtraction is the opposite of addition, square rooting is the opposite of squaring or the inverse of squaring something. A logarithm is the inverse of an exponential function. Okay. Logarithms are used if you are not sure of what power produces a given number. So, for example, 2 to the what power equals 32. This is a situation where we would use a logarithm. Okay. You could guess and check for this problem. It's actually true that 2 to the 5th is equal to 32. But what we're going to do today is we're going to take this exponential statement, 2 to the x equals 32, and we're going to transform it into a logarithm, and then that's something that we'll be able to type into our calculator. Okay. So here's what this is going to look like. Okay. A logarithm, again, is trying to find a missing exponent. The exponent is the number you are trying to find. So that's why whatever number's all by itself on the other side of the equal sign is that missing power or that missing exponent. Okay. LOG just stands for log, but every logarithm has what's called a base number. Okay. And that base number is written as subscript, meaning it's just small and towards the bottom. So log, in this case, I would read this as log base 10 of x. And then the number that goes in the logarithm is what's called the argument. Okay. This is all brand new, but we're going to see how it works, and it'll make a little bit more sense in a minute. But every logarithm has a base number, and then it has an argument right after it. And most of the time, that argument is also going to be a number. Okay. So one thing that just want to throw out there, if you see a logarithm without a base number, okay, if you see LOG with no base number, you should, it is base 10. It was agreed upon by some old mathematicians that log without a base number would be used for base 10 because base 10 is used so frequently in the metric system and a lot of other places. But we're going to use, if you just see log of x, understand that that missing base will always be base 10. Okay. And so like right here on the calculator, if you switch over to the calculator quick, if you hit this log button, there is no base with it because it's just base 10 is used so often that there's a dedicated button for log base 10, but you don't have to actually type the number 10 in. Okay. So what we're going to do is we're going to try typing this into the calculator. What is log base 10? I'm going to write it in for now just so we remind ourselves. What is log base 10 of 100? I do log base 10 of 100. I get 2. And log base 10 of 10,000, I get 4. Okay. So let's break down what this actually means. Okay. Just here's my base number, right? That was mentioned up here. The number in parentheses is the argument. And then the number on the other side, or what we get out of the calculator, is the exponent. So this isn't a coincidence. Okay, log base 10 of 100 is equal to 2 because 10 to the second power is equal to 100. So the 2 was the missing power that we didn't know. And that's why the calculator gave us the number 2 for that. Okay. Log base 10 of 10,000, this next statement right here, log base 10 of 10,000 is equal to 4. And the reason that's true is because 10 raised to the 4th power is equal to 10,000. Okay, so there's this really tight-knit relationship between exponents or exponential expressions and equations and then logarithms. And they work together super closely. And so that's really what the bulk of today's lesson and video is how can I take something that's exponential and write it as a logarithm and then vice versa. Okay. So again, if you have something like a statement like this, log base 2 of 32 equals 5. Okay, this is actually from the, not the warm-up, but the next slide. And the reason that's true is because 2 to the 5th power is 32. So the definition of a logarithm comes from exponential statements. So if you say 3 to the 4th power is equal to 81, okay, I'm not just saying that, that's true. 3 to the 4th is equal to 81. The way I could rearrange that as a logarithm is log base 3. Okay, so whatever the base of the, and that's also called, this number right here, this 3, is also called the base. So that's a convenient, convenient parallel between the two, is that the word base is used for both 3 to the 4th. The 3 is the base number, and then the small number with the logarithm. Okay, so log base 3 of 81 equals 4. And then for just 1/3, or just for a third example, 6 to the negative 2nd power is equal to 1 over 36. So I could rewrite that and say log base 6 of 1/36 is equal to -2. Okay, so it's really just rearranging those parts. So if you would please pause the video real quick. I want you to try taking a couple logs and writing them as exponents, and then taking a couple exponential equations and writing them as logarithms. So with a log, there's my base number. So I start there, raised to that power, so 5 to the 3rd power equals the argument of the logarithm. So 5 to the 3rd equals 125, which if you want, you can double check in the calculator. Sure enough, that's true. So 6 to the 4th equals 1296. I'm going to rewrite as log base 6 of 1296 is equal to 4. Okay, that's just, again, I'm not solving anything. I'm just rewriting that statement using a logarithm. So log base 7 of 1 over 49 is equal -2. And remember, with a log, whatever's on the other side of the equal sign is the exponent that goes with it. All right, and then finally, -5 to the -2 is equal to 1 over 25. You could write this as log base -5 of 1/25 equals -2. What I will tell you is that you will never see a logarithm with a negative base. So you could rewrite that as a log, like you could physically write it down, but mathematically it doesn't make sense. Um, and we could go into it, but I'm not going to in this video. Base can't be negative. Okay. So in order to use logarithms, the base has to be a positive value. Okay. So writing exponential equations in logarithmic forms. Okay. So I want to do the exact same thing. We're not going to actually solve it, but I just want to get used to, as we go into 7.5, I want to get used to writing this as a logarithm, even though it has a variable in it. So if I were to go log, here's my base is 8. Next is my argument, which is comes from the other side of the exponential equation. Equals, nope, not 8, equals x, which is the exponent. Okay. Again, all I've done is rewritten it. Okay. If I had x to the 5th equals 298, I could do log. The base would have to be x of 298 is equal to the exponent, which is 5. And finally, 3 to the 7th power equals x. I would say log base 3 of x equals 7. Okay. So that's just the same idea, rewriting exponential to logarithmic, but using variables as well. Okay. So here's where we want to go with logarithms. Okay. If you see something like log base 2 of 8, we want to know, what does that equal? Okay. What is that value equal to? And there's a couple different ways you can do it. I'm going to show you how to use the calculator in just a second, but let's think about, what is this asking? Okay. Log base 2 of 8 is equal to what number? If I took this statement and rewrote it like we've been doing the last 5 minutes as an exponent, okay, or as an exponential equation, it would be 2 to the x power equals 8. So sometimes you can do this by hand. Okay? 2 to what power equals 8? And you could start guessing and checking in the calculator. 2 to the 2nd, that's equal 4. 2 to the 3rd, that's equal 8. So that would tell me that the missing number, or the missing exponent, has to be 3. Okay. I'm going to show you in just a minute how you can just type that into your calculator, and you'll get the calculator will tell you that 3 is the value of it. So if we use that same thinking here, what is log base 4 of 1? So 4 to what power is going to give me 1? This is kind of a goofy, or kind of a tough question, because 4 raised to what power gives you 1? If you tried a couple things, 4 to the 1st power, well, that's equal 4. 4 to the 2nd power is going to be 16, so I'm going the wrong way. If I did 4 to the -2nd power, I get a decimal, which is good. But actually, the sweet spot is any number raised to the 0 power. Anything raised to the 0 is going to output the number 1. So in this case, x would be 0. Okay. So that's what it means to evaluate a logarithmic expression, is you are trying to figure out what power would make the statement true, or what exponent would make the statement true. Okay. This change of base formula is something you will use You don't need to know necessarily where it comes from, or how it was derived. Okay, but the problem is almost no calculators. If I wanted to type this into the calculator, almost no calculator has a log base 2 button. Okay, the only button on the calculator that's immediately apparent is this log button, and again, this is going to be base 10. So what the change of base formula allows us to do is it allows us to use any calculator we want to figure out, and I'm talking phone calculator too, any calculator we want to figure out a logarithm. So uh, simply all you're going to do is we have to break that one logarithm into two separate logs and divide. And how you're always going to do this is the log of the argument, which is the write the number in parentheses if it's in parentheses. And notice that this is base 10. Okay. So you're going to do just regular log base 10 of the argument, and you're going to divide by log base 10 of the base that you were looking for in the original problem. Okay. So I'll show you how to use this twice, and we'll wrap this up. So if you wanted log base 4 of 15, this would be saying 4 to what power equals 15. And this is going to be really tough to do because it's a decimal, and the decimal is not going to be nice. So what I'm going to do with this is I'm going to rewrite this using this change of base formula. So I'm going to write this as log base 10 of the argument that I had divided by log base 10 of the original base I was given, which is 4. Now you notice I put these in parentheses. It's not written in parentheses in the formula, and maybe I should have written it that way. But you have to make sure you close up the parentheses, especially after this first log. So log 15 divided by log of 4 gives me 1.953. Okay. Now, again, just to check our work, what that means is if I go 4 to the power of 1.953, I get a number that's very, very close to 15, 14.99. This is why it's important that with logarithms that you don't round too early. If you just said like 1.9 or 2.0, that's not going to equal 15. It's going to equal 16. So we're gonna kind of add to the number of decimals that we hold on to when we're dealing with logarithms. So log base 2 of 47, again, 2 to what power is equal to 47 is what this is asking. So I'm going to do log of 47, and I'm going to divide by log of 2. Log of 47 divided by log of 2. So just double check, 2.2 raised to the power of 5.55 will give me 46.85, which really isn't even that close to 47. So we should probably go to the third decimal point, which is 5.555. Okay. So logarithms, you can type in the calculator using this change of base formula, and it tells you the missing, oh my God. It tells you the missing exponent. So go ahead and pause real quick. See if you can use the calculator to plug these in. You should have gotten all whole numbers for this. Log of 243 divided by log of 3. Maybe these aren't awful. I'm second guessing myself now, but log of 243 divided by log of 3. So that's equal to 5. Log base 2 of 256 is 8. And log base 7 of 1 over 343. So log 7. Oops, I did too many. Dang it. Too many parentheses. I didn't realize that it already gave me a set of parentheses. Log of 7 should be -3. equals -3. Okay. So to summarize, what are logarithms? How do they relate to exponents? Okay. Logarithms are used to find missing / unknown exponents. Log base is what that's called. This is called the argument equals, and this is the exponent. All right, that'll do it. On to 7.5.